Welcome to the High Voltage AI Podcast. I'm Alex Reed.
And I'm Emma Quinn.
And this is the deep dive, your direct route to being truly well-informed. We take a stack of articles, research, and, well, our own notes, and we extract the most important nuggets of knowledge and insight, basically custom-tailored for you.
Yeah, our mission is to help you quickly grasp the essentials of complex topics without feeling overwhelmed. Think of us as your expert guides, helping you cut through the noise.
Exactly. We want to help you understand what really matters in the information you need to master.
That's right. We're here to help you connect those critical dots and see the bigger picture, especially when it comes to the intricate challenges in electrical engineering.
Absolutely. Now, this entire week, we're doing something a little different. We're part of a special week-long series featured in the PXRD newsletter on Substack.
Oh, right, the PXRD series. That's a great resource.
It really is. For those unfamiliar, PXRD is a leading publication specifically for electric utility professionals. And this series is all about educating utility engineers on the different types of overhead and underground construction. Why we choose them, what their characteristics are.
The fundamentals, but also the nuances.
Exactly. Today's Monday, and we are kicking off the week by taking a deep dive into heavy angle framing.
And our mission for this deep dive is to truly get to grips with the critical nature of heavy angle construction. We're going to explore why it's not just an option, but really an absolute essential for maintaining system integrity.
And how it differs so much from standard approaches, right?
Precisely. Because as you'll discover, these structures often tackle some of the most demanding structural challenges any engineer in the field will face. Seriously demanding.
Okay, so let's unpack this then. What's really at the heart of the problem here? What kicks off the need for this specific type of framing?
Well, it boils down to those moments when your conductor routing, in an overhead electrical system, demands a significant angular deviation, a sharp turn.
A sharp turn. We're generally talking about turns that exceed, maybe 30 degrees? Is that the usual threshold?
Yeah, typically beyond 30 degrees is a common rule of thumb, though it definitely varies. When you hit those kinds of angles, standard through construction where the line just passes through a tangent structure, it just won't cut it anymore.
It becomes inadequate.
Totally inadequate. And that's precisely when heavy angle construction steps in. It's not just a preference. It becomes a necessity to maintain the entire system's integrity.
Okay, so the angle is the trigger. But what's actually happening physically that makes a simple pole insufficient?
Well, what's truly fascinating here is the physics behind these angular forces. You see, in a straight section of line, the tension forces on the conductors largely balance each other out. It's a relatively stable situation, pulls equally in both directions.
Right, canceling each other out at the pole.
Exactly. But the moment those conductors change direction sharply, that balance just disappears. Poof. Instead, these angular changes create something we call a resultant force.
Resultant force? Okay.
Yeah, imagine a single powerful force that effectively bisects the angle formed by the two conductor directions. It's almost like the system is trying to, pull itself back into a straight line, and this resultant force is the sheer magnitude of that pull towards the inside of the corner.
So this resultant force, does it just scale linearly with the angle, or are we talking about something more dramatic, something engineers really need to watch out for?
Oh, it's definitely nonlinear and quite dramatic. It ramps up fast. Consider a standard 90-degree corner, a right turn. That resultant force can become approximately 1.4 times the individual conductor tension on each side.
Wow, okay, 1.4 times. That's significant.
It is, and for even sharper angles, say 60 degrees or less, that multiplier just escalates further. We're not talking about minor nudges here. These are concentrated loads that could easily snap a standard pole without very specific, robust structural support.
So without proper heavy angle design, you're looking at a serious, imminent failure risk.
Absolutely. It's a critical structural challenge.
Okay, given forces of this magnitude, how do we engineers actually tackle them? What's the go-to solution that truly shines in these high-stress scenarios?
The most reliable and widely adopted approach for heavy angle construction is essentially to provide independent support for each side of the angle with its own set of down guys. This is what we often call the independent guy wire solution.
Independent guy wire solution.
Yeah.
Okay, what's unique about that? How does it fundamentally change how we think about the structure compared to just trying to, beef up a single pole?
Well, the real genius of this independent guy wire approach lies in its fundamental philosophy. You basically treat each conductor direction as if it were an independent dead-end structure.
A dead end, like where the line just stops.
Exactly. Now, for listeners who might not be in the weeds with this every day, a dead-end structure is essentially a point where the line fully terminates and all its tension is wholly anchored to the ground. So in heavy angle construction, using this method, you'll have a side one guy wire dedicated solely to supporting the tension forces coming from the first conductor direction.
Okay, just handling that pull.
Just that pull. And it transfers those loads directly to the ground through its own anchor system.
And then presumably you have a side two guy wire doing the exact same thing for the other conductor direction.
Precisely. It has its own entirely separate load path to the ground. So it's really two completely separate support systems, each handling its own specific load rather than one single system trying to manage a combined, much more complex force.
Ah, I see. It's like you're breaking the problem down.
You are, and this independent approach offers several critical advantages that are really worth deeply considering. First, the true brilliance here is load isolation.
Load isolation, meaning
each guy wire handles only the forces from its respective conductor direction. It completely eliminates those complex and often unpredictable load interactions that can happen, across the pole structure in less robust designs. Those interactions can lead to failures.
Okay, so it simplifies the forces on the pole itself, too.
It does. It dramatically simplifies the engineering and enhances reliability. It's like having two separate, highly specialized emergency brakes, each dedicated to its own side.
Gotcha. What else?
Second, you gain significant maintenance flexibility. Because each side is structurally independent, individual sides can often be de-energized and worked on without compromising the structural integrity of the other direction. That's crucial for routine maintenance, emergency repairs, or even planned upgrades.
Right, you don't have to take the whole corner out of service necessarily.
Often, yes. And finally, a huge benefit, which really impacts system-wide resilience, is failure redundancy.
The backup plan.
Kind of, if for some unforeseen reason, one guy wire system were to fail. Maybe an anchor pulls out, maybe a wire snaps due to damaged dauber. The other side maintains its structural integrity.
So the whole structure doesn't just collapse.
Exactly. This prevents a cascade failure, which could otherwise bring down multiple sections of the grid. That's a massive win for overall grid reliability. It's about designing resilience and sort of compartmentalization directly into the system.
That makes a lot of sense. So what does this all mean for you, the engineer working in the field? When is this specialized construction absolutely necessary? I mean, it's not for every subtle curve in the line, right? There must be triggers.
That's a really important question. And yeah, the answer is driven by several key factors. As we touched on, angular deviation is primary. Generally, if the conductor routing changes direction by more than 30 degrees, you're definitely looking at heavy angle construction.
The 30-degree rule of thumb again.
Right, but that exact threshold can actually shift based on other considerations. Conductor tension is another big one.
How so?
Well, circuits with higher tension conductors, think bigger wires, longer spans will require heavy angle construction, even at smaller angular deviations.
Because the resultant forces are just inherently greater to begin with.
Exactly. That intuition holds up. A circuit with extremely high tension might need heavy angle support, even for, say, a 20-degree turn, whereas a lower tension distribution line might be fine closer to 30 degrees.
Yeah.
It's all about the magnitude of that resultant force you have to safely manage.
Okay. Angle and tension. What else?
Environmental loading also plays a significant role. If you're designing in areas prone to high wind, heavy ice loading, or maybe even seismic activity, you might need heavy angle construction at smaller angles.
To maintain adequate safety factors against those extra stresses.
Precisely. You need that extra margin. And finally, system criticality.
How important the line is.
Yeah. For circuits that are deemed critical, perhaps they feed a hospital, a major data center, or are a backbone transmission path engineers might proactively opt for heavy angle construction even at smaller angles than technically required by force calculations alone.
Just for that extra peace of mind.
It's a proactive measure, safeguarding essential services, ensuring maximum reliability. It's about risk management.
Okay, so once you've determined that heavy angle construction is needed, based on those factors, what are the crucial calculations and planning elements engineers must master for these structures? It sounds like there's a lot more going on than just putting up a pole and stringing a wire.
You're absolutely correct. It demands a meticulous attention to detail and, a deeper level of analysis than tangent construction. One of the first and most critical steps is the resultant force calculation.
Getting that number right.
Exactly. Engineers must precisely calculate this force based on the specific angle of the turn. The exact conductor tensions involve considering sag and temperature effects too, and crucially, factoring in any applicable environmental loading like wind and ice. This isn't a ballpark estimate. It needs to be precise because it informs everything else.
Does that precise calculation ever uncover surprising challenges? Like, does it sometimes show you need even more support than you might intuitively expect?
Oh, absolutely. It often highlights just how immense these forces can become, especially under combined loading conditions. It definitely pushes engineers to sometimes go beyond initial assumptions or standard tables.
Okay, so you have the force. What's next?
That precise calculation directly leads to guy wire sizing. Each guy wire, and remember, we have at least two for these angles, one for each effective dead end, must be sized for the full tension from its respective conductor direction, plus safety factors.
Not some kind of shared or balanced load.
No, that's a crucial distinction. You're not sizing for some balanced load you might assume in tangent construction. You're sizing for the full independent pulling force of the conductors on that side. This also directly impacts anchor requirements.
Right, the guys have to attach to something solid.
And those guy anchors have to handle these full, unbalanced loads, which often means they require larger, deeper, or maybe more specialized foundations than you'd use for standard installations. You need to ensure that load is transferred safely and effectively deep into the ground without, pulling out.
And I'm guessing fitting all this hardware in, especially the multiple guy wires, creates its own set of problems. Clearance management, maybe.
You hit the nail on the head. That's often where the real headaches begin. It can look like a spaghetti junction sometimes. Multiple guy wires running in different directions, often with multiple circuits potentially on the same pole, creates complex clearance challenges.
Challenges to what? Other lines? Buildings?
Both. Clearances to other utility lines, clearances phase to ground, phase to phase, and clearances with the surrounding environment like buildings, roads, or even just uneven terrain. This demands incredibly careful planning, 3D thinking sometimes, and often requires specialized hardware or unique configurations to ensure everything maintains appropriate separation and safety codes are met. It's not just about strength, but also about the precise spatial relationships.
It sounds incredibly complex. Given how critical and, frankly, complicated these structures can be, are there other ways to manage these challenging angles? Or is the independent guy wire approach always the only or best go-to?
That's a good question. While the dual independent guy wire approach is very common and highly reliable, especially for distribution and lower transmission voltages, there are indeed other solutions. Each has its own specific applications and, importantly, trade-offs.
Like what?
Well, one alternative is using strain structures. These are often multi-pole arrangements, like H-frames or three-pole structures, designed to distribute angular forces across several points, rather than concentrating them on one pole with guys.
Spreading the load.
Exactly. They can be very useful for extremely high loads, like on major transmission lines, or in situations where installing guy wires simply isn't feasible, maybe due to tight right-of-way or difficult terrain for anchors.
Okay, what else?
Another option is using heavier pole classes. This involves deploying substantially stronger, often larger diameter or steel poles, specifically designed to handle significant angular forces without needing external guy support.
Just a really, really strong pole.
Basically, yes. While this eliminates the need for external guys and their anchors, which it can be good aesthetically or for space reasons, it significantly increases the cost of the pole itself. And it might still necessitate larger, more robust foundations for the pole because all the bending force is concentrated at the base.
Right. The force still has to go somewhere. And what if you just want to avoid the whole overhead mess entirely in a tight spot or a really sharp corner?
Well, that leads to underground transitions. You can basically convert the overhead lines to underground cable through the angular section. Dip down, run underground, pop back up.
Takes the structure out of the equation.
It entirely eliminates the structural challenges associated with overhead angular forces, yes. But, and it's a big but, it comes at a considerable expense, often much, much higher than any overhead solution. Plus, it introduces its own set of underground-specific challenges like splicing, heat dissipation, and accessibility.
So costly, but sometimes necessary. Any other overhead tricks?
One more common strategy is using intermediate structures. Instead of making one very sharp 90-degree turn, for example, you might break it into two 45-degree angles using an additional pole in between.
Making several smaller turns instead of one big one.
Exactly. This reduces the structural demands, particularly the resultant force, at each individual angle point. It turns one big, complex problem into several smaller, more manageable ones. It can be a very elegant solution where space allows for the extra structure.
This really highlights that heavy angle framing isn't just about efficiency or convenience, is it? We're really talking about the core of system reliability here. The stakes feel incredibly high with heavy angle design.
Absolutely. And that raises an important point about the truly critical nature of heavy angle design. You see, these structures often represent foundational critical points in electrical systems. They're frequently where multiple circuits converge or where major transmission paths change direction.
Key intersection.
Precisely. Because of this, a failure at one of these heavy angle locations can lead to widespread outages and significant system disruption, far beyond just the immediate area. This makes proper structural design absolutely essential. There is, frankly, no room for approximation when you're dealing with the concentrated forces involved in angular construction.
You simply cannot afford to be wrong.
You really can't. The consequences are too high.
So the normal rules, the standard practices you use for designing straight sections of line, they just don't apply here. It's a whole different ballgame, requiring specialized focus.
That's spot on. The normal rules of through construction or tangent construction no longer apply. This type of design requires specialized knowledge, meticulous calculations, and careful structural analysis to ensure reliable performance under all operating conditions, whether it's everyday tension, high winds, or heavy ice accumulation.
It's about preparing for the worst-case scenario.
It is. Ultimately, whether you're navigating tricky property line constraints, overcoming challenging terrain obstacles, or simply meeting specific system routing requirements dictated by load centers or other infrastructure, heavy angle construction provides that fundamental structural foundation. It's what allows us to safely navigate the sharp, directional changes that real-world electrical systems frequently demand, keeping the power flowing reliably where it needs to go.
It really underscores the engineering precision needed behind the scenes. So here's something to think about. What stands out to you about the incredible precision and foresight required for these critical junction points in our power grid? It's a true blend of physics, material science, and practical on-the-ground engineering. That's all for today's deep dive. Remember, this is just the beginning of our week-long series with the PXRD newsletter. Make sure to tune in tomorrow, Tuesday, when we'll be diving into vertical framing.
Another really important construction type. Looking forward to that one.
Me too. If you'd like to leave feedback or have any questions about today's topic or anything else, feel free to reach out to us. You can email me at alex.reed.power.podcast@gmail.com.
And you can reach me at emma.quinn.power.podcast@gmail.com. We do read all the emails.
We do. Thanks again for joining this deep dive.